Large reasoning models, LRMs, they've been making some truly incredible headlines lately, haven't they?
Absolutely. We're seeing AI models tackle really complex logical mathematical problems, stuff that's genuinely hard.
Yeah, and sometimes even beating typical human scores on tough benchmarks, like
Mm.
frontier math, seeing amazing results there.
It definitely creates this powerful impression, this illusion of competence almost. But, the real question lurking underneath and what our source material really digs into is not what they did, but how they did it.
How do we actually know they're reasoning correctly? Is that the worry?
That's the core anxiety, yes. Because
Yeah.
almost every current test battery we use for this focuses only on the outcome. Did it get the final answer right? Yes or no. It's usually just exact match evaluation.
Okay, that seems fine maybe for a simple quiz, but why is getting the right final answer on a hard math problem? Why is that not enough when we're trying to measure actual intelligence?
Well, because the model can get the right answer for completely the wrong reasons, and that's a critical difference.
Huh.
Think about it. In these tests, models can latch on to superficial patterns, or maybe just pull answers from the massive amounts of data they were trained on. They're using really sophisticated retrieval, not necessarily step-by-step derivation.
So they're effectively memorizing their way to the answer sometimes.
Exactly.
Yeah.
And that can really inflate how well we think they're doing. It makes them look smarter than they perhaps are in a reasoning sense.
Right. So it's like that student who's read the textbook cover to cover, recognizes the problem type, knows what the answer should look like.
Mm-hmm.
But if you ask them to actually derive it step by step, maybe on a slightly different problem, they couldn't do it.
Precisely. And in genuine mathematics, the proof, the process, that's everything, not just the final number.
So this outcome-based approach just doesn't cut it for judging real reasoning, especially in math or logic.
Totally unsuitable. Anywhere the process of reasoning matters, just checking the end result is flawed. And that's where our sources introduce this new benchmark, ProofGrid.
Okay, ProofGrid. What's the idea here?
It's a massive new set of tests, over 10,000 problems, designed specifically to stress test reasoning by making the models actually construct and verify formal proofs. It demands rigor.
Interesting. So it's a shift, right? Moving away from just right or wrong to looking at how the model gets there. The sources seem to argue that current benchmarks aren't even testing the right kind of intelligence.
That's a really key point they make. They bring in this concept from psychology, the difference between crystallized and fluid intelligence.
Okay, let's unpack that.
Yeah.
Crystallized versus fluid. Why is that distinction important here?
So crystallized intelligence is basically what most current benchmarks measure. It's all the stuff you've learned, your accumulated knowledge, facts, problem-solving techniques you've been taught or picked up.
Like the model's huge internal library of everything it read during training.
Exactly. It can retrieve facts, apply known methods, and these models have read, well, pretty much everything digital, so their crystallized intelligence is enormous.
Giving them a huge advantage on tests that tap into that knowledge base.
A massive advantage. But ProofGrid aims for the other side, fluid intelligence.
Which is?
That's your innate ability to reason, to solve novel problems you haven't seen before, where you can't just rely on stored knowledge. You have to figure it out from first principles.
And how does ProofGrid target that?
By using pure symbolic logic problems. These are completely abstract. They're about form, not content. There's no real-world knowledge that helps directly. It forces the model to use pure reasoning.
Because there's no answer to just look up in his training data if it's just symbols and rules.
Precisely. It cuts through the crystallized knowledge to get at the underlying reasoning competence.
And that's needed because, as the sources point out, models like GPT-4 are hitting the ceiling on older benchmarks, right? They're getting almost perfect scores.
Yeah, many benchmarks are getting saturated. We need harder, more structurally complex challenges to actually see where the limits of these powerful models still lie. ProofGrid aims to be that challenge.
Okay, so let's get into the structure of ProofGrid itself. What kind of pure logic are we talking about? Is it super obscure stuff?
No, actually, they chose systems that are fundamental but also powerful enough to encode really complex ideas. Specifically, propositional logic, they have two versions, PL1, and a more complex PL2 and equational logic, EQ1.
Can you give us a quick feel for those? Propositional logic.
That's about basic logical statements, things being true or false, and how they connect with and, or, not, if, then. PL2 gets tricky because it allows encoding complex combinatorial problems like reasoning about paths and graphs or counting things based on parity, stuff that older benchmarks couldn't really handle well.
And equational logic.
That's about proving that two mathematical expressions are equivalent, usually by applying rules to transform one into the other. Think of it like simplifying algebraic expressions, but in a very formal, rigorous way.
Right. Now, a big hurdle with formal math proofs in AI has always been the proof systems themselves. Things like Lean or Isabelle, using other benchmarks. They're powerful, but have a really steep learning curve, even for humans. How does ProofGrid handle the rigor without needing that huge overhead?
That's one of the really clever parts. They developed this minimalist proof language they call NDL, natural deduction language.
Minimalist.
Yeah, the entire set of rules for writing proofs in NDL is so simple and compact that it can be fully described right in the prompt given to the AI model.
Wait, so the model learns the rules on the fly from the prompt rather than needing extensive pre-training on the proof system itself?
Exactly. It minimizes the chance the model is just memorizing the proof system. The focus stays on applying the logic to solve the specific problem. And this NDL system actually mirrors how humans often reason informally, using techniques like assuming something to see where it leads, conditional proof, proving something by showing its opposite leads to a contradiction, or breaking a problem down into cases.
So it demands things like tracking assumptions, understanding scope, putting multiple steps together logically.
Yes, all of that. And the scale is different too. You mentioned composition. The depth of reasoning required is way beyond older benchmarks.
How deep are we talking? The sources said older ones often capped out at fewer than 10 steps.
Right. Proof-Griard problems routinely require proofs with dozens of steps. And for the really hard ones, we're talking over 100 logical steps needed to reach the conclusion.
Wow, over 100 steps.
Yeah.
That's a serious test. Keeping track of everything across that many steps requires understanding the global structure, not just local moves.
It absolutely is. And that leads into the really novel tasks ProofGrid includes to specifically test that structural understanding.
Ah, yeah, this sounded fascinating. They have standard tasks like writing proofs, checking proofs, but then these new ones. The first is proof infilling or unmasking. Tell us about that.
Okay, so imagine you have a complete correct proof. For the infilling task, they take that proof and just hide certain key parts.
Like redacting words in a document.
Kind of, but for logic. They might mask the final conclusion of a step, or the specific rule that was used, or maybe an assumption that was relied upon, or even one of the prior lines cited as justification.
And the model has to figure out what's missing.
Exactly. It becomes a constraint satisfaction problem. The model has to infer the missing symbol or step that fits perfectly, respecting all the rules of logic and the syntax of the proof language.
So it's not just solving the original problem, it's demonstrating it understands the internal mechanics of how a valid proof works.
Precisely. High accuracy here suggests the model has a real, robust internal model of logical structure, not just surface pattern matching. It suggests it gets the rules.
That's clever. And the second novel task, proof gap filling. How's that different?
Gap filling zooms out a bit. Instead of masking tiny individual pieces, it creates gaps at the subproof level.
Subproof level.
Yeah. They might remove an entire chunk of reasoning, maybe a single crucial intermediate lemma, or a whole block of steps that were done under a temporary assumption, or even a sequence of consecutive lines.
Whoa. So the model sees the beginning of a proof section, the end of it, and has to generate the entire missing logical bridge between them.
Exactly right. It has to write a potentially complex proof fragment that logically connects the surrounding steps, possibly involving nested reasoning or case analysis within the gap.
That sounds incredibly difficult. It tests not just executing steps, but understanding the overall flow and coherence of the entire argument, even across nested structures.
It's a major test of understanding global proof structure and high-level planning.
Okay, so ProofGrid sounds seriously tough, demanding this fluid intelligence, deep reasoning chains, structural understanding. How did the big AI models actually do? Time for the reality check.
Well, the results really highlight just how hard this is. You mentioned saturation on older benchmarks like GPT-4o scoring over 98% on Pronto QA, basically perfect.
Yeah.
On ProofGrid, the picture is starkly different. The overall accuracy rates are dramatically lower, even for the very best models out there.
Give us the numbers. How low are we talking?
So, across the entire benchmark, a strong model like DeepSeek R1 only managed about 35% accuracy overall.
35%.
Yep. And GPT-4o often seen as a top contender, just 13% overall accuracy.
13. Wow. That's a huge drop from near perfect scores elsewhere.
Yep.
What about on those really complex PL2 problems you mentioned earlier?
Even tougher. For the proofwriting task on PL2, things like DAG pebbling, De Bruijn formula's only one model. Grok 4 managed to even break 50% accuracy, getting 51%. Most were much lower.
Okay, so this benchmark is definitely finding the limits. It's differentiating performance in a way the older tests just couldn't anymore.
Absolutely.
This huge gap, near 100% on old tests, down to 35% here. Where are the models actually failing? Is it just random errors, or is there a pattern?
It's interesting. The analysis and the sources suggest they still make basic elementary errors, sometimes like misapplying a rule, losing track of an assumption scope, simple mistakes almost. But when their researchers looked at the natural language comments, the models sometimes generate, alongside their attempts, like a 4 Mini trying to explain its plan for a dig problem, they often found the strategy was perfectly correct.
Huh. So the model could, like, describe the right approach in English, outline the main steps, identify the key lemmas needed.
Yeah, the high-level strategic competence often seemed to be there. It knew what needed to be done, conceptually.
But it couldn't translate that plan into a sequence of formally correct logical steps.
That seems to be the core issue. It suggests the LLM part is maybe good at the conceptual planning, the intuition, but fragile when it comes to rigorous step-by-step symbolic execution. The linguistic side is strong, the formal logic side is brittle.
Which points toward,
Well, it points directly towards the kind of neurosymbolic future the researchers propose.
okay, neurosymbolic, how would that work? Combining neural networks with symbolic logic systems.
Exactly. The idea is to use the LLMs for what they seem good at, being the high-level planner. Let the LLM propose the overall proof strategy, the key intermediate goals.
And then,
Then you pair the LLM with a classical symbolic system like a formal proof assistant or a dedicated solver. These tools are built for rigor. They act as the executor.
so the LLM suggests a plan, and the symbolic tool tries to execute it step by step, enforcing the actual rules of logic.
Precisely. It becomes an iterative process. The LLM proposes, the solver checks or executes. If it fails, the LLM might revise the plan. It mirrors how human mathematicians often work, having an intuition, then carefully formalizing it.
That makes intuitive sense, leveraging the strengths of both. But isn't adding that extra layer, that symbolic engine, going to be complex? Getting the LLM planner to talk effectively to the symbolic executor sounds like a challenge in itself. Is that really practical today?
That's a very fair question. Yes, there's complexity in that interface, but the argument is that the symbolic engine guarantees rigor. It won't let an invalid step pass. So the complexity burden shifts to teaching the LLM how to generate plans or instructions that the symbolic tool can understand and verify.
So the symbolic tool enforces the rules, the LLM learns to work within them.
Basically, yes. And while it's still an evolving area, the potential payoff is huge. Getting outputs that have both the conceptual insight of an LLM and the formal correctness guarantees of a symbolic system. The sources suggest this combined approach is probably the most promising path forward for truly reliable reasoning.
Okay, wrapping this up then. What's the big takeaway from ProofGrid in this whole deep dive?
I think the main point is that ProofGrid really shifts the focus. By demanding actual proofs, not just final answers, and by testing that fluid intelligence with abstract problems, it gives us a much clearer and frankly more sobering picture of where AI reasoning capabilities truly stand.
It emphasizes the integrity of the reasoning process itself.
Exactly. And it confirms that the major hurdle left isn't just more data or bigger models, it's achieving deep, structural, verifiable reasoning.
And for our final provocative thought for you, the listener, think about software. For decades, the dream in computer science and formal methods has been verified software programs mathematically proven to be correct.
The absolute gold standard for reliability, especially for critical systems.
Now, imagine if AI models get good enough, perhaps through these neurosymbolic approaches, to not just write code, but to generate a formal, machine-checkable proof that the code is correct alongside it.
Proofs that we could independently verify using trusted tools.
If AI could do that reliably, it wouldn't just be helpful, it could fundamentally change software development. We could potentially build systems with unprecedented levels of guaranteed safety and robustness, making AI-generated code truly trustworthy.
That ability to prove correctness. Yeah, that really could change everything.